Welcome to Chapter 2, Part 6. Now that we have introduced resonance structures, we've talked about moving from one resonance structure to another via the common patterns. We want to address something that comes up when we have resonance structures of differing stability, right? Some structures will contribute equally. For instance, that very first example that we keep coming back to, there is no significant difference in these two resonance structures. They both have a single carbon-carbon bond, a double carbon-carbon bond, a plus charge on a carbon atom. So as far as their energy goes, they would each be equal energy, and therefore they would contribute to the hybrid equally, right? So these are equal contributors. That is not always going to be the case. We are going to have resonance structures that are very different. For instance, when we looked at an example of a carbonyl, right, and its resonance structure that has formal charges with a plus charge on the carbon and the bonding pair of electrons now up on the oxygen as a lone pair. These are both valid Lewis structures. They are both resonance structures of the same molecule. And so the reality is a mixture somewhere, a hybrid of the two. However, these are not equal in energy. I chose this as an example to start with because it's a little more intuitive. The one that's neutral and has all of its octets filled is going to be the major contributor. So the hybrid is going to look more like the major contributor. Tends to be lower in energy. And the one with the formal charges over here is going to be a minor contributor. And it's higher in energy. We'll pretend that I spelled that right. There we go. Now, that one's a little bit more standout. It's not always as obvious. And so we're going to have some rules. And these rules you are going to have to follow in order to determine major and minor contributors. So again, the following rules, are going to be listed in order of importance. We're going to go over these rules now, and it's important that you memorize them in order. All right, so number 1, we are going to be looking at octets. Whichever resonance structure has the greatest number of full octets will be the major contributor. Now, for us, that is pretty much going to come down to if a plus charge is on a carbon or not, because carbon is the only element in that row that we are in row 2 that we are looking at that could have less than an octet. So if you have an example, and I'm going to just draw the bond line structure of it here, where we have an oxygen. Okay, let me just start over and not be so messy. Okay, here we have an oxygen with 2 lone pairs and a carbon with a plus charge. We also have a resonance structure where there is a double bond and the plus charge is on the oxygen. These are not equivalent because the carbon does not have a full octet, right? And in this one, all of the atoms have a full octet, right? Except for hydrogen, which is fine. And so more significant, major contributor, lower energy is going to go to the guy with the full octets, right? So this one is going to be more important. Again, it's going to be a hybrid of the two, but the hybrid is going to look more like the major contributor. All right, so that would mean that this is a minor contributor over here. Okay, so that's the first thing you're going to check for. lack of full octet. So that's your carbocations. Rule number 2, we are going to look for fewer formal charges, right? The fewer the formal charges, the more stable, the lower energy, the more significant, right? Or the major contributor. So if we look at this example over here, we looked at an example in that previous slide, right? But in our previous example, when we looked at the carbonyl resonance structures, they're both overall neutral, right? Because to be resonance structures, they have to have the same overall charge. But this has no formal charges, and this one has 2 formal charges, right? You can also think about it as formal charges closer to 0. In this case, we have no formal charges. We have a +1 and a -1. We have a +1 and a -1. So we know that this one is going to be most significant. We also know that this one is in the middle and this one is least significant. Now, how do we know that? Well, in this case, these both have formal charges of +1 and -1, but this one, the carbon does not have a full octet, right? So we can actually start to combine the rules. So we would have already known that this was least significant because the carbon doesn't have a full octet, where 1 and 2 both have full octets all around. And then we can differentiate between the most significant and just sort of our middle guy here by formal charges, right? So you can do octet first and then formal charges. That's going to be the next important. And then number 3, we're going to look at okay, before we move to number 3, I'm sorry. I don't want to forget this. There are resonance structures that we may consider insignificant. However, if I asked you to draw a valid Lewis structure, a resonance structure, this is valid. It's just by splitting the charge up this much, and it still has a -2 overall charge, it's just considered insignificant. It's going to play such a small role in the overall resonance hybrid that it will often be left out. But I'm not sure why they put an X here. It's still a Lewis structure. It's not a very good one. Okay. And then rule number 3, it's going to have to do with charge and where the charge is located. So first of all, negative charge is more stable on the more electronegative element. Is more stable on the more electronegative element. So let's take a look. Electronegative. Ooh, we are getting sloppy here. I'm sorry. Electronegative element. All right. So for instance, when we have this, I'm going to do the bond line structure of that first example. We have a negative charge on an oxygen with a double bond out to that carbon. So we have an allylic lone pair. If we move that allylic lone pair towards the double bond and the pi electrons out, you'll get quicker with that as you practice those patterns. That oxygen is neutral now, but this carbon now has 2 hydrogens and a bond to carbon, so it has 3 bonds and a lone pair. The negative charge is on the carbon. Well, oxygen is more electronegative than carbon. So if we go through our rules, in both of these resonance structure, you have a full octet, right, on the oxygen and all the carbon. So that's not helpful. They both have 1 minus 1 formal charge. So rule 2 doesn't help us. So rule 3, the negative charge is on the more electronegative element, right? Oxygen can hold more electron density, or hold it. It wants to hold it more than carbon does. So this one's going to be our major contributor or more significant. It's going to be lower energy, more significant. These are just all the different ways we can talk about this. So this one is going to be minor in comparison. It's going to be higher in energy, or it's going to be less significant. Right? It's just the different ways we can talk about that. Now, as an extension of Rule 3, if you have a positive charge, and now we can't be talking about on carbon here, because if you have a positive charge on carbon, you don't have a full octet, and that's going to hop to Rule 1, right? Rule 1, that's why you have to do these in order, because the octet rule is more important than the charge on a particular element. So if you have a positive charge, and we'll put not on carbon, we're not talking about on carbon, it's going to be more stable on the less electronegative element. So in that second example, we have a positive charge on our oxygen here, and nearby we have a nitrogen. So if you notice, we have an allylic lone pair, right? So that lone pair is going towards the double bond. The pi bond electrons are popping out onto the oxygen. That gives us a neutral oxygen because now it has two lone pairs. We have a double bond to the nitrogen that has two hydrogen. So it has four bonding pairs. The positive charge is on nitrogen. Oxygen's more electronegative, so it is pulling that electron density harder. So it's actually going to be more stable or more significant, right? Or the major contributor. Lower energy, just all the different ways we can say this, when the plus charge is on the nitrogen, right? So this one would be less significant, or the that's not pretty, or the minor contributor, right? If we're looking at major and minor. So you want to know these three rules, and you want to know them in this order. So check for octets, check for overall numbers of formal charges, and when all else fails, which element is holding the charge? If none of these rules help us, then they're probably equal contributors, right? Because look what we have here. We have one carbon that does not have a full octet. Well, we have one carbon that does not have a full octet. They both have a +1 on one element or one atom. And the plus charge is on carbon in both cases. So we go all the way through those rules. We find no difference. They're going to be equal contributors. If we practice here, we can draw a couple of, we'll blow this up. We'll draw a couple of resonance structures for each form and then talk about contribution. Now, to start off, I want to put in my lone pairs. A nitrogen with a negative charge has 2 bonds and 2 lone pairs. So I can easily, I have two patterns I can do. I have an aromatic ring, so I could just alternate those double bonds, which means I would still have 2 lone pairs and a negative charge on nitrogen. Or I have an allylic lone pair, and I can move those electrons toward the double bond, and then I can move the pi electrons out onto the carbon, right? Knowing those patterns makes things go a lot more smoothly. Now let's draw the result of this. I didn't touch these 2 double bonds, so I'll leave them alone. I made a double bond to nitrogen, so now it has 1 lone pair, 3 bonding pairs, so now it's neutral. This carbon out here has a hydrogen on it, and now it also has a lone pair, so that's where my negative charge wound up. You can draw more, right? You can move that lone pair around the ring because now it's an allylic lone pair to this double bond here. But I'm going to stop just so we can talk about major and minor contribution. These two structures are identical in terms of number of octets filled, formal charges, and formal charge on which element. So these two are equal. However, this one is different, right? Octets are all full. Formal charge, there's one atom that has a negative charge, a -1, a -1. So we have to go to rule 3. The negative charge on the nitrogen is going to be more stable than a negative charge on carbon. Why? Because nitrogen is more electronegative. So these two are equal, and together they are both major contributors, right? Or more significant. This one is going to be less significant, right? So I can start to draw resonance structures and I can start to analyze them, right? I know that the overall hybrid isn't going to be split equally among every resonance structure if there are differences based on these 3 rules. And so I definitely recommend going in. You can find, this is a practice the skill question if you want to do some more practice, which I recommend. Pop into the Wiley Plus Access. You can do this problem here, as well as some other practice, the skill, and skill builder problems. We are going to talk about MO theory later. We've talked about the term delocalized already. When it comes to hybridization, it is trickier when we think about sp3 and sp2 hybridized. It is tricky when we have resonance structures in the mix. What you were taught in Gen Chem has some exceptions. Everything we learn tends to have exceptions in chemistry. And this is one of those times. It looks like if we just analyze the nitrogen in this structure, it's sp3 hybridized. And in this one, it's sp2 hybridized. Well, in reality, if you have a resonance structure where it's sp2 hybridized, it's just going to be sp2 hybridized overall. It's the only way the resonance works. This isn't going to be an issue for you until Organic 2. We will revisit that and spend more time on it. For now, if you come across a question that asks about hybridization, whatever, if you have sp3 and sp2, the one that has the lower number, that's going to be what it is overall. So you're going to get sp2. And we are not going to worry about that. We'll revisit this in chapter 3. So that is going to be the end of chapter 2. Highly recommend, really, really strongly encourage you, do a fair amount of resonance practice. If you are not able to get the, correct answer repeatedly, this is going to be something that comes back and haunts you later. So do the practice now. I have practice up on eCampus. Throughout the week, I'm going to add at least one video of me doing more resonance problems. There are also videos in Wiley Access embedded in the textbook. So you can actually watch somebody else work through some problems as well. Come see me if there's anything else I can do for you. See you in chapter 3.